All right, learning goal number 4. Let's do it. Be familiar with the heat capacity of solids. And this is, again, another review from 361. We're going to add just a little bit of touch of our new material. So if you recall the equal partition theorem, this says in a sample of temperature T, all quadratic contributions to the total energy have the same mean value, which is, do you guys know it? Do you remember it? 1/2 K Boltzmann T. So 1/2 times KBT. And so you can see with my pictures here of these molecules, depending on if it's a linear molecule or a nonlinear molecule, will have different total energy contributions. So you can see here with the linear molecule, it's able to rotate uniquely in 2 different dimensions. And if you recall, the internal energy as a function of temperature will go as, our 0-point energy, UM0, plus, and now we've got to add up all of those degrees of freedom, right? So remember, we have 3 translational degrees of freedom, 1/2, 1/2, 1/2. Then we're going to add in these 2 rotational degrees of freedom, another 1/2, 1/2. So that gives us plus 5/2. I'm going to write KBT. I was about to write RT, but we know for our, we'll go with it. For our molar quantity, right, I wrote UM, so we'll stick with RT. So we can say is 1/2 KBT, or remember, for 1 mole, we could say that that's 1/2 RT. So now what I also want you to recall is heat capacity, in this case, the constant volume heat capacity, is the partial of U with respect to T at constant V. So now if we look at the heat capacity of this linear molecule, right, easiest derivative we'll take all semester, that just becomes 5/2 R. And so now, if you recall with this non-linear molecule, the internal energy goes as the following. Let's write that again. That was a little sloppy. UM at 0 Kelvin. And then now we still have our 3 translational degrees of freedom to give us 1/2, 1/2, 1/2. But now you can see this molecule can rotate uniquely in 3 extra dimensions. 1/2, 1/2, 1/2. 6 halves makes 3, so that is 3 RT. And if we were to look at the heat capacity of this molecule now, we recognize it's just the derivative of that function with respect to temperature, so that becomes 3R. Okay, so now, if you recall with solids, the ideal heat capacity for a solid is 3R. We get that from the following. So if you can imagine a very simple cubic lattice, then I'll try to draw here very carefully so we know exactly what it is I'm drawing. And if I put an atom in the middle of that lattice there. So now what's different about this in the solid state versus the gas state, it's got nearest neighbors, right? Front, back, left, right, top, bottom. It's got nearest neighbors. So that means when this vibrates in the positive X or negative X or the positive Z or the negative Z or the positive Y or the negative Y, those are all going to be unique contributions, 1/2 KBT or 1/2 RT. So, and recall our solid is not free to translate around like a gas molecule. So it's just vibrating against its neighbors. So that gives us 6 degrees of freedom, 6/2 K Boltzmann T or 6/2 RT, which will give us 3 RT for its internal energy, and thus its heat capacity is 3R. So now if we notice here this expression that I have, there it is, CV as a function of T equals 3R, and now it's being multiplied by this function of temperature. So in the limit when this function approaches 1, our solid approaches its ideal heat capacity. And as you can see right here on this graph, CV divided by R, as you can see when the solids raise in temperature, they approach that value of 3R. And you notice that we have the Einstein formulation and the Debye formulation. Technically, the Debye formulation is more accurate, but I don't want to get into too many of those details for the purpose of this class. So here I've given the Einstein formulation. And so now you can see that function of temperature is given as the following. So let's talk about what all these things are. So theta is h nu divided by k Boltzmann. So h is its usual meaning, that's Planck's constant. K Boltzmann, that's the Boltzmann's constant. And now this new value right here, that is our lattice vibration. So that is the quantized thing that's going on in this solid. So that's what's making it vibrate in those 6 unique degrees of freedom. If we inspect the units of this equation, we'll see that the Planck's constant is a joule times a second. The frequency is 1 over seconds, and K Boltzmann is a joule per Kelvin. So the seconds and the seconds cancel, the joule and the joule cancel, and we're left with 1 over Kelvin, which is just Kelvin. So what this quantity represents is what we refer to as the Einstein temperature. And that Einstein temperature is the temperature at which our solid begins to flip over to its more classical value. So now if we look at this x-axis, there I'm going to circle that number 1. So T divided by theta E, right? That puts us at the Einstein temperature. And if I travel on this graph up here, you can see that represents an inflection point in this graph where it begins to approach its classical value of 3R. If we look at the other chunks in this equation, upon quick inspection, we might recognize there's also a partition function going on there, right? So if I substitute that theta E value into this expression, right, that's going to become the exponential of h nu divided by 2 times kBt. So, and if you recall, right, and our partition functions, those go as energy divided by kBt. So h times nu gives us energy divided by kBt. Okay? And so as we might imagine now, this Einstein temperature is purely a function of the lattice vibrations of our particular solid.